Time for more practice. We're gonna get good, so we ace the test. Woo! Yeah! Of course, you know what that means. More problems. More problems we do, more familiar we get with how to do problems, the better we're gonna be. So, let's do more problems. All right, here we go. Number 1. Solve the following differential equation. Ty prime plus t plus 2y is t e to the power t cubed minus t. And the initial conditions, y of 1 equals a third. All right, well, what kind of problem do we have here? Well, this is a nice problem for us. It's a linear first-order differential equation. It's our bread and butter in some sense. We love these kinds of problems. They're very straightforward. It's a nice technique. And so we just have to remember the process. And the process is the following. So step 1, make the coefficient in front of y prime to be 1. And so to do that, we'll divide through by t. So we're going to say, all right, y prime plus 1 plus 2 over t times y is e to the power t cubed minus t. Okay, great. And the reason we're doing this is we're setting ourselves up because the technique involved is to find an integrating factor. And we do that by grabbing this coefficient, but we have to, before we can grab that coefficient, we have to make sure that that's a 1. And so now we're going to do the integral, 1 plus 2 over t. And then we're going to take e to that power. All right, so let's do that. So what do we have? Well, this will be the same as e. Integral of 1 is t, and then plus 2 natural log t. And when we're doing our integrating factor, we don't need to worry about the plus c. So that's nice. And we should clean this up. This is the same as e to the t times e to the 2 natural log t. But of course, the 2 can be moved up. And that's really natural log t squared. And you have e to that. And so this becomes t squared e to the t. Right? T squared e to the t. So that's our integrating factor. Okay, so now the idea is we're going to take this factor and multiply it by that expression. And let's see what we get. Well, we get the following. We get t squared e to the t times y prime plus, now we can multiply the t squared through there. You'll get t squared plus 2t e to the t times y equals, on the other side, t squared e to the t cubed minus t. And, well, we can clean this up. Now the key thing is, and the reason this all works, the beautiful fact, is that the left-hand side is a derivative. This is the derivative of t squared e to the t times y. And on this side, well, we can actually do a little bit of cleanup. See how we have that e to the t, this e to the t cubed minus t? We can combine them together. We add the exponents. The plus t minus t cancel, and we'll end up with t squared e to the t cubed. All right, great. And now we're ready to do integration. Okay, well, one of these integrals will be very easy, and the other one won't be too bad either. I mean, we got to be able to do it, right? Otherwise, we couldn't answer the question. So, okay, so what do we get? We'll get t squared e to the t y, that's the left-hand side, is equal to, now on the right-hand side, what we'll do is do a substitution, because we see a function inside a function. So we'll let u equal t cubed, then we'll say du is 3t squared dt. Well, we can move the 3 over to the other side. So 1/3 du is t squared dt. So that really what this is the integral of e to the u, du. Integral of e to the u is e to the u, which means that the integral of the left-hand side, don't forget the 1/3, is 1/3 e to the t cubed. And now you do need a plus c, because this is a point where you need a constant. Now, we have to do two things. We need to solve for y and need to solve for c. And you can do those in either order. In this case, it seems pretty straightforward to plug our initial conditions in and help us solve for c. So, all right, if we plug in our y of 1 equals 1/3, well, that says everywhere you see a t, put a 1. Everywhere you see y, put a 1/3. Well, what do we have? We'll have 1 e to the 1. So we get 1 times e times 1/3 equals, on this side, 1/3 e to the 1 cubed, which is still e, plus c. And what do we see? Aha! Lo and behold, we see that c is 0. Now, you might say, oh, great, we didn't need c. No. You still have to run through and check. If you omit checking that c is in fact 0, you could lose points. You should lose points. It's an important part of the process. But now we're basically done. So what's left to do? Well, now we know c is 0, divide through, and we get our final answer. So notice when we divide by e to the t, that's the same as, e to the minus t, multiplying. So you can combine. So you have e to the t cubed minus t. And then downstairs you have the 3 and that t squared. And we're done. That's it. That's it. Wow. That's cool. That worked out pretty well. Okay, wonderful. Well, we like these problems. We like these problems. Hopefully we'll see some of these on the exam, right? Well, there's always the hope. So, all right, moving on. Number 2. So, a tank with a total capacity of 80 gallons is initially filled with 40 gallons of pure water. At time t equals 0, a valve is opened that pours brine into the tank at a rate of 8 gallons per minute with a salt concentration of 1 pound per gallon. At the same time, a second valve is also opened that empties well-mixed brine out of the tank at a rate of 4 gallons per minute. Now, when the tank is completely full, both valves are turned off and determine the amount of salt that will be in the tank after the valves have been turned off. All right. Now, this is one of those things like, whoa, there's a lot of words. I thought this was a math class. I didn't come in here wanting to learn to read essays, but what we're doing here is we're describing things. And an important skill in mathematics is saying, oh, here's this real-world phenomenon. Let me translate it into some mathematical descriptions so that we can more readily do some analysis here. All right, so let's start again, but as we go through, let's draw ourselves a picture so we make sure we have a visual about what's going on. So we have a tank, and it has a total capacity of 80 gallons. So we'll draw ourselves a little tank here. So here's our tank. So the capacity is equal to 80. And initially, it's filled with 40 gallons of pure water. Okay, so that means at time 0, it's half full. So, okay, so here's our water at time 0. All right, great. Now, we put some notes here. So, at t equals 0, we have 40 gallons. We'll put some units here. And it's pure water. Well, notice that we're talking about salt. And so, 0 salt. Okay, that'll be important. And now, we say, great. A valve is opened, and it pours brine into the tank. Okay, so now we have essentially salt water coming in. And what happens? Well, this is going at 8 gallons per minute. And notice the salt concentration is 1 pound per gallon. Well, if it's 1 pound per gallon and there's 8 gallons, that says there's 8 pounds of salt per minute, right? That's how much is going in. Now, on the other hand, we say, oh, there's a second valve. The second valve is doing what? Well, it's somewhere near the bottom, and it's emptying out. Now, this is at 4 gallons per minute. Okay, so that's the setup. And now, let's look at what we want to do. Well, it says, when the tank is completely full. Well, notice the tank is half full, and the amount coming in is greater than the amount going out. So what that means is over time, it's going to rise up. All right, well, how long will it take to get full? Well, what's the difference between the in versus the out? And the answer is, well, a net 4. So every minute that passes, we get 4 more gallons. And how many more gallons do we have to fill to be full? Well, there's 40 gallons between the initial amount and the capacity, which means we have 10 minutes. Okay, so what we want to know, and our question we can ask, and we'll phrase it this way, question, amount of salt at time t equals 10. Okay, great, good. Now that's our question. So now we know what we're after. So, well, let's set up our equation here. It's a differential equation, and we're going to figure things out. So where do we begin? Well, we need to begin with the name. So what do I mean? Well, what do we call our amount of salt? Well, it's an amount, so we could call it A for amount. I mean, any name is fine. So let's let A of t equals the amount of salt at time t. All right, great. Now, what do we know? We know A of 0 is equal to 0. How do we know that? Because we're told at time 0 there's no salt, pure water. And we also can talk about how the salt changes. So when we talk about changing, that's A prime. Now what do? Well, we say, let's compare how salt enters and leaves. Because salt doesn't spontaneously create, it has to come in or go out. Well, we know how it comes in. It comes in at a nice steady flow. So it comes in at a constant rate of 8. All right, so that's our in. And in other words, that's how salt gets added. So we of course, add it. Now, how does salt get removed? In other words, subtract. Well, it gets removed out of this other valve. Now, what's going on here with this second valve? Well, notice we didn't talk about how much salt leaves per minute. We said, well, 4 gallons leaves per minute. And we say, okay, well, 4 gallons, it's well mixed. So that means, however much salt there is, we take that proportion out. But what's the right proportion? Well, now we have a sort of a slightly different question. How much fluid, if you like, how much brine, is in the tank at a given time? We can say, well, there's 40 initially, and every minute that passes, we add 4. So there's 40 plus 4t. That's the amount of fluid in the tank at a given time. So now the claim is you look at 4 over 40 plus 4t. And the claim is that is what? Well, that's the proportion of the fluid that leaves. So that's 4 gallons out of 40 plus 4t gallons. Okay, Now, that's the amount of fluid, that's the proportion of fluid that leaves. And because it's well mixed, that's also the proportion of salt that leaves. And so, if you multiply that by A, that's how much salt exits the system. All right, so 4 over 40 plus 4t times A. This is going out. All right, great. Well, now let's rearrange, clean this up. Doesn't look so bad. Notice that you can cancel some 4's in that first equation. And what do we have? Well, A prime, this will come across as a plus, and 1 over 10 plus t times A is equal to 8. It's the same kind of problem we just did. This is a linear first order equation. So we say, all right, well, let's take a look at the integrating factor. So, well, we're going to use this first piece here. So we're going to take e to the integral 1 over 10 plus t. Well, that's e to the natural log 10 plus t, which is 10 plus t. That's our integrating factor. All right, so we get the following. We multiply through. We have 10 plus t, a prime, plus a is equal to, well, multiply 10 plus t here, 80 plus 8t. And on the left-hand side, this is nice. By design, this is the derivative of the integrating factor times our function. So now we can integrate both sides very, very quickly. It's a very straightforward integral. No surprises, no surprises. So that will equal integral of 80 plus 8t and dt. And we end up with 10 plus t times a is equal to 80t plus 4t squared plus c. Now we pull out the fact that we know at time 0, we have 0. So we say, okay, great, at time t equals 0, we get the following. We get 10 times a equals, 10 times a of 0, which is 0, equals 0 plus 0 plus c. So c equals 0. Well, perfect. Perfect. Now, we're almost done. We're in the home stretch because we have what we need. We actually have the following explicit formula. A is equal to, we know c equals 0, divided by 10 plus t. So 80t plus 4t squared divided by 10 plus t. So the last thing is plug in 10. And we'll see a of 10. Well, that's 800 plus 4 times 100. So 400 over 10 plus 10. Okay, so 800 plus 400 is 1200. 10 plus 10 is 20. And if you take 1200 divided by 20, we get 60. And there's the answer. 60 pounds. 60 pounds of salt are in the tank after the valves get turned off. All right, good. Now, we can ask ourselves a quick question. Does this seem fairly reasonable? And actually, we can do one quick observation. Notice that we have 8 pounds of salt coming in every minute, and we run it for 10 minutes. So the maximum it could be is 8 times 10, which is 80. And that assumes that all the salt were staying. But the salt is also leaving that because it's being well mixed. So we know it should be below 80. So 60 is actually fairly reasonable. It's below 80, but not by a huge amount. So if we had gotten an answer like 200, we'd be like, whoa, wait, something's wrong. And we would stop and say, let's go back and check our work, because we want to make sure we get good, reasonable answers. Because, numbers mean things, and we want to make sure that what comes out at the end is something meaningful. That's why we're doing all this. Of course, we want it to have meaning. All right. Number 3. Ooh. All right. Here we go. A spring with a spring constant K of 18 newtons per meter is attached to an object, which in turn is connected to a damper, which will dampen at a force of 6 newtons for every unit of velocity in meters per second. Now let x of t denote the motion of the spring. And part A says, well, given that the system exhibits critical damping, determine the mass of the object. So we have this spring, there's this spring here, and there's a spring constant, there's a damper attached, slowing it down, and we have the weight is just right. It's on that like magical threshold so that it experiences critical damping. Now, if you make the weight lighter, then it'll oscillate. And if you make the weight heavier, it'll be overdamped. And so there's that magic point. Okay, so how do we find it? Well, what we do is we say, okay, let's recall how springs work. Now, if we wanted to add a picture, we could quickly draw ourselves a little picture. Here's our little object, and there's our spring, and then it's attached to some sort of a damper, which, again, I like to think of is somehow it's something that's pushing through, like, say, a fluid of some sort down here. And so the spring constant we know, and the damping we know, we just don't know the mass. And there's no external forces being described here, and so we're going to not assume that there's any external forces. And so that makes it really nice. So in particular, it says, okay, if you remember our boxes, you have something x double prime plus something x prime plus something x equals, normally you'd have external forces, no external forces, so we put 0. Now, where do our numbers slot in? Well, the spring constant, that goes into that slot. It goes attached to the x. So, great, 18. No problem. The damping, that goes with x prime, because damping is related to how fast the object is moving. And so, that should be attached to velocity. So that's 6. And the mass, well, if we knew it, it would be right there. So that's the differential equation for this particular spring system. Now, according to what the mass is, you'll have different behaviors of the spring. And so we're saying, well, we know we have a very particular type of behavior, and that's the critical. So next thing is to say, all right, translate this into an equation, and we turn it into our characteristic polynomial, our r's. So we say, okay, this would translate into mr squared plus 6r plus 18 equals 0. And what we want is we want this, and we haven't said this out loud yet, and when do we know we have critical damping? We need to have repeated roots. That's the key. So we want this to have repeated roots. Now, what that really says, hey, we need to have it be the case that this is a perfect square. Okay, so that's what we're going to do. Make this into a perfect square. Now you might say, well, how do we do that? Well, here's the moral. Let's do completing the square and say, okay, if we were to complete the square, how would it have to work out? Now, when we do completing the square, we like to have a 1 as our coefficient of the square term. We can do that, just divide through by m. So, r squared plus 6 over m, r plus 18 over m equals 0. And now we run the process. So if the leading coefficient is 1 in completing the square, the next thing you do is you go to the coefficient of your linear term, r in this case r, divide that by 2. Okay, so 6 over m divided by 2 would be 3 over m, and you're going to square that, and that would be what needs to go there. So, in order for this to work out, in order for the completing the square to work perfectly, we need the 3 over m quantity squared has to be equal to 18 over m, or, if you like, 9 over m squared has to equal 18 over m. And now, we'll move the m squared across, move the 18 across. We get that our mass, because the m squared over m is m, and 9 over 18 is a half. So this is the answer to part A. Mass is a half. Great. Perfect. We're halfway through, right? Well, there's 2 parts. So we did part A. All right. Great. Now, part B. So now we say, hey, we're actually in doing great because we know what our mass is. We can just keep going with the problem, right? So our mass is a half. And so what we really have here is we have r squared, 6 over m is the same as 12 r, and 18 over m is 36. Or, if you like, that's the same as saying r plus 6 squared equals 0. And so our repeated roots are -6 and -6. All right, that's good. We know what our repeated roots are. All right, now, the one thing, I'm going to pause and say, the roots should have negative real parts. Always, 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 always for springs. And if the roots don't have negative real parts, go back and check your work. Because if your roots had positive real parts, your spring would be going crazy, and that's not how springs work. Okay, but we're fine. So what does that say? Well, it says that our x of t has to have the form some constant e to the minus 6t, and then it's repeated, so we got to do our bumping up. So there's some constant b times t e to the minus 6t. And that's the behavior of the spring. All right. And remember, it is possible for a spring to not have sines and cosines. That's if the damping is sufficiently large. There's no more sines and cosines. So, this is great. So we have our behavior, but we don't have a and b, but we also have some initial conditions. x0, x prime 0. All right. Well, let's talk about x prime really quickly. That's minus 6a e to the minus 6t plus b e to the minus 6t minus 6b t e to the minus 6t. Now on this last part, what happened is we did the product rule. Derivative of t is 1. That's where you get 1 times e to the minus 6t. And derivative of e to the minus 6t, the minus 6 comes down. All right, so x of 0, we know that's 4, and that's equal to a plus b. Okay, so 4 equals a plus b. X prime is 0, that's negative 39. Well, what does that equal to? Well, minus 6a plus b. Oh, whoops, why did I say a plus b? Just a. I forgot to plug the 0. Sometimes you're going too quick. Slow down. So 4 equals a. Well, that's easy. That says 4 is a. All right, great. And x prime 0 minus 39 equals minus 6a plus 4. But we know what a is. It's minus 24. Add 24 to both sides. Say, oh, hey, great. So b is minus 15. All right, great. So now we know a, and we know b. So we now know the complete behavior of the spring. So we can say x of t, and since these both have e to the minus 6t, let's go ahead and pull it out. That's e to the minus 6t times a, which is 4, and then plus b times t. Well, that's minus 15 times t. And what are we looking for? Well, we want to determine the unique, which means there's just one time that the spring will be in the natural position. So the natural position, you might call it the resting position, where the spring wants to be. So it wants to have 0 offset. And that's what it means. In other words, find t where x of t equals 0. Well, if I want to have x of t equals 0, the only way that can happen is if this part equals 0. Because I can't have e to the minus 6t equals 0. But now we see, oh, you add 15t, divide by 15, and we see that t has to equal 4 over 15. And that's the time. So at that one moment in time, we are going to pass through. And so what will happen if you were to track the motion of the spring is it starts above, goes down, and then slowly in the long run moves back towards 0, but never goes back above. And that's the behavior. That's it. And that's the answer. We're done. So for part A, we have the mass needs to be 1/2. For part B, time equals 4 over 15. And another problem done. These are fun. These are fun. It kind of makes you wish this was on the real exam, right? It's like, yeah, we can do these. Well, I think if you can do these, I hope you can do the ones on the real exam too. All right. Number 4. Solve for x of t and y of t, satisfying the following system. X prime equals 5x plus 9y, and y prime is minus x minus y, where x of 0 equals 10, and y of negative 3 equals 0. Now, before we get too far, I want to point out something a little bit like, that's a little different. We normally haven't done this. Notice the initial conditions. And it's not that we've never done initial conditions before, but see, the initial condition for x and the initial condition for y are happening at different times. Is that allowed? Well, we'll get to that. We'll get to that. Yes, it's totally allowed. Okay. All right, spoiler alerts. All right, but let's begin. Now, the way that we want to approach this is we want to use our tools using eigenvalues. So we want to use the eigenvalue method because it's a really powerful way to handle systems. So the first thing we do is we translate this into a nice sort of setup where we have eigenvalues involved. And we say, okay, well, that's the same as x prime equals, 5, 9, minus 1, minus 1 times x. So these numbers in this matrix coming from the coefficients that we have there. All right, well, this is our matrix A. So here we have our matrix A. Say, all right, that's our matrix A. What we want is we want the eigenvalues of A. So how do we find those? What's the technique? Well, okay, so we need to do a computation. And namely, we're going to take the determinant of A minus lambda I. And let's see what that turns out to be. So we're going to set to 0 the determinant A minus lambda I. So that's the determinant of 5 minus lambda, 9, minus 1 minus lambda. So that's 5 minus lambda, minus 1 minus lambda, subtract minus 1 times 9. Okay. Multiply out. Minus lambda times minus lambda is lambda squared. Then you have minus 5 lambda plus lambda makes minus 4 lambda. Then we have minus 5 plus 9 plus 4, which is lambda minus 2 squared. So our eigenvalues are 2 and 2, which means we have repeated eigenvalues. Now, the moral of the story is if you have repeated eigenvalues for a 2 by 2 matrix, and if it's not a boring matrix, that means you're going to have to deal with a missing eigenvector. Now you might say, but what's boring, Steve? A boring matrix would be something that looks like the identity matrix. So where you would have like a 0 in the upper right and a 0 in the bottom left. In that case, like, yeah, you have enough eigenvectors. But it's like saying like, oh, x prime equals 5x and y prime equals 5y. Okay, all right. Well, there's no interaction going on. Boring. But this is not boring. So it's like, So we're going to have to deal with missing eigenvectors. So let's do this. So we go in, we have our missing eigenvector hat on, and we say, well, all right, we're going to sort of go through 2 rounds. So round 1 was we find the eigenvector, and round 2 was we find the generalized eigenvector. So the key is to start with a minus lambda I. Now we know the eigenvalues are 2, so plug in lambda equals 2. Because you have a minus lambda I, you just need to plug in what lambda is. So you have 3, 9, minus 1, minus 3. And we're looking for v1, v2, where we get out 0, 0. Okay, so this is the find the eigenvector. Well, now what's going to happen? Well, no surprise, if you look at the 2 equations that are really being encoded here, you have 3v1 plus 9v2 equals 0, and minus v1 minus 3v2 equals 0. And you're probably like, wait, those are the same equations. You're right, they are the same equations. Say, all right, just get rid of one. I don't know, let's get rid of the top one. I like the fact that there's smaller numbers in the bottom one. So you just pick one, it doesn't matter. And okay, that says, hey, that says v1, that's equal minus 3v2. So if you look at your vector, v1, v2, well, it has to look like minus 3v2, v2, which is v2 minus 3, 1. So that's your eigenvector. And in fact, we've said, look, there's only one. Up to scale, there's only one. Now, if you're ever paranoid and like, I'm not really great, super comfortable with doing eigenvector computations, how can I be sure I got the right one? Multiply the matrix by the vector and ask the question, is the new vector that comes out, is it a scalar, the one you started with? And if the answer is yes, you're like, okay, you did a great job. Keep going. Keep going. All right, so that's round 1. Ready for round 2. In round 2, we have to kick it up a notch. And what we do, well, we're going to look 3, 9, minus 1, minus 3. And now W1, W2 equals, and what you put over here is the vector minus 3, 1. All right. Well, again, you're going to end up with 2 equations, but there's going to be redundancy. So in other words, it's really the same equation, just slightly offset. Well, when I say slightly offset, just a different multiple. Now, say, all right, we'll get rid of one of the equations. Again, the top one seems busy. Bottom one seems simpler numbers. We only need one solution, and there's infinitely many. I recommend just try to find something super simple. And so, given that there's infinitely many, the way I look for something super simple is like, well, if I set one of them to 0, do I get a really nice answer for the other value? And if I look, I say, oh, set W2 equals 0, W1 equals minus 1, that's super clean. And we say, yeah, let's go with that. And so we'll say, all right, W1, W2, we can just make negative 1, 0. All right, good. So, recap, this part, negative 3, 1, eigenvector. This part, negative 1, 0, is our generalized eigenvector. All right, well, now, where do we go? Where do we go from here? Well, the next part is to say, well, what's the solutions look like? And that would be the following. So we have x, and this x, you can't tell by my handwriting, but I wrote it in a bold way. It's really representing a vector. And so in particular, it's representing the functions x, t, y of t. So what does that look like? Well, it looks like the following. Our first part, so some constant, our e to the eigenvalue times t, and then times our eigenvector, minus 3, 1. And then we have our second part. So b, again, e to the eigenvalue t. And now this is where the bumping goes on. So make sure you get this part right. So you're going to take t times your eigenvector plus this other piece down here, minus 1, 0. All right, now let's mush this all together. You might at this point say, hey, isn't this a great time for us to plug in our initial conditions? And normally our answer would be, yes, this would be a wonderful time to do that. Except, not this time. And that's because these times don't match. So it makes more sense to pull it apart. In fact, there's a good reason to do that. So let's go through the process of pulling it apart, and then let's talk about why it's a good idea to do that. So we can say this is, and I'm just going to put everything into, top entry, bottom entry. So we get minus 3a e to the 2t, and then here we will get, this will be minus 3t plus 1 times b e to the 2t. So you got the b e to the 2t, and you have minus 3t minus 1, so that's where the minus is coming from. That's the top part, bottom part, a e to the 2t, and then plus, here we'll just have b times t e to the 2t. All right, so what we've done here is we've taken the vector entries and we've just put it all into one big vector. So, move the scalar multiples in, do your addition, clean it up. This is what you get. So, we have that x of t is the top row, minus 3a e to the 2t minus 3t plus 1 b e to the 2t, and y of t is the bottom, a e to the 2t plus b times t e to the 2t. Now, let me pause here and say it's important that regardless if your initial conditions were at the same point or not, you really do want to break it up. Because the way the problem is stated is it doesn't have them together in a vector. We introduced that. It was a tool for us to help us solve it. So if we introduced it, we need to sort of undo it at the end and say, well, our answer should look like something x of t and something for y of t. And so make sure that if you have a problem like this, present it in this format, that you don't leave your answer as a vector. Pull it apart into the two parts. And that way, they won't have any excuse to take off a point. We don't even want to give them even a, we don't even want that to cross their mind. Like we want them to give us all the points. All the points. That's the goal. That's the goal. Now let's use our initial conditions. Okay, so what do we have for some initial conditions? Well, we're told x of 0 equals 10. All right, well, let's, let me grab a good pen here. All right, so x of 0 equals 10. Now, the nice thing about plugging in 0 is things simplify quite a lot. E to the 0 is 1, and 0, turns out, is equal to 0. So that would be minus 3a from the first term, and here, from the second term, minus b. So minus 3a minus b. All right, well, That's all right. No worries. How about y? Well, we get y of minus 3 equals 0. Now here, like, we're going to get some crazy numbers because you have these exponentials. Well, just go with it for right now. A e to the minus 6 minus 3b e to the minus 6. But here's the nice thing. Both terms have e to the minus 6, and it's equal to 0. So you can divide, and therefore, you say, because of that 0, that really says, a minus 3 times b equals 0. Aha! So what does that say? That says a has to be equal to 3 times b. Okay. Well, all right. That's perfectly fine. So if a equals 3 times b, then what we can do is we can come back to the first equation and we say, that says 10 is equal to 3 times a would make this minus 9b minus b, or minus 10b equals 10, so b is minus 1, and if b is minus 1, a is minus 3. Okay, good. Now, finally, what do we do? Well, our last step is to now write down our answer, and all right, we'll write it. There's a little space up here, and so here we go. So anywhere where we see an a, we put negative 3. Anywhere we see a b, we put negative 1. So we have minus 3 times minus 3. So you get that x of t is equal to 9 e to the 2t. And then we have the b minus 1. And so there's a minus there. So plus, and then we have 3t plus 1 e to the 2t. And y of t, well, what's that? Well, you have a, which is minus 3, so minus 3 e to the 2t. And then b is minus 1, minus t e to the 2t. Well, you can do a little bit, factor out the e to the 2t's, and you have 3t plus 1 and plus 9. So you end up with 3t plus 10 e to the 2t. And here, you can factor it out, and also factor out a minus. You get minus t plus 3 e to the 2t. And there we go. There's our answers. 3t plus 10 times e to the 2t, and negative t plus 3 times e to the 2t. All right, well, that worked out pretty nicely, I think. Yeah, I like that. That came out in the end. I thought it came out really nice. Beautiful, beautiful. And number 4, which means halfway done. Woohoo! Halfway. Well, means there's still halfway to go. Okay, well, halfway. Number 5. Find e to the at for a is 3, 2, minus 9, minus 3. And use this to solve x prime equals ax, where x of 0 is minus 1, 3. Okay, all right, here we go. Now, how do we do this? Well, normally when we find e to the at for a equals that, well, what I like to do is I'd like to say, let's start solving this. And as we solve, we can start filling in a fundamental matrix, because e to the at is sort of a very special fundamental matrix. And so we're sort of after the fundamental matrix that makes everything work nicely. All right, well, let's get going. So first thing is, what are my eigenvalues? So we're going to set 0 equals, and determinant 3 minus lambda, 2 minus 9, minus 3 minus lambda. So that's 3 minus lambda times minus 3 minus lambda, and subtract 2 times negative 9. Well, that's lambda squared. And then we'll have a minus 3 lambda plus 3 lambda. So the lambdas cancel. Oh, nice. Minus 9. Right, 3 times minus 3 minus 9 plus 18. Minus 9 plus 18 makes plus 9. So lambda squared plus 9 equals 0. So what's lambda? It's going to be a little bit complex. Exactly. So lambda is plus or minus 3i. Okay, great. All right, now what? Well, now we know our answer's going to involve something with sines and cosines. And the real nice is this is pure imaginary. And because it's pure imaginary, it really is just sines and cosines. There's no other, e to the stuff floating around. So that's good news for us. So the next thing is find n eigenvector. When you have complex roots, like we have here, we don't actually have to find both eigenvectors. We just need one. All right, so let's do positive 3i. So for lambda equals positive 3i, it's important to remember which one you're working with. We're going to take our a minus lambda I, so 3 minus 3i, 2 minus 9 minus 3 minus 3i. And we're multiplying that by a b, and we want to get 0, 0. And, well, what you end up with is you have two equations. Now, the thing is, when you have complex numbers, it's a little bit harder to see this, but it is still the case that if you have eigenvalues, and you're doing your eigenvectors, eigenvalues, that in fact, there's redundancy. So these two equations are not that different from each other. And the way we use that is just we say, okay, let's just pick one, and we'll take it out. All right, well, I like the 2. That's a smaller number, so I'll take this one out. And now we start thinking, okay, how do we find a choice for AB? We only need one choice. We just need one eigenvector. And one way to think about it is to say, oh, well, 3 minus 3i times A equals minus 2 times B. And now pair it up. And by that, what I mean is, the A can be the minus 2, and the 3 minus 3i, that can be the B. And so we say, aha, here's an eigenvector that works, namely AB is minus 2, 3 minus 3i. There we go. Now, it's important to take this and to pull it apart. And, okay, so this would be the same as minus 2, 3, plus I, 0, minus 3. Okay, so we found our eigenvector, and we've pulled it apart. Now, the magic. What you do is we're going to take these eigenvalue and eigenvector, take them together, and use them to find our two solutions. And the way it happens, well, lambda equals 3i, we would do e to the lambda t, but using some basic facts, that's cosine 3t plus I sine 3t. So again, this is our e to the lambda t, and now we're going to multiply that by our vector, which we've pulled apart, negative 2, 3, plus I, 0, negative 3. And again, here's our vector. So it's e to the lambda t times v. In other words, it's the same thing we do whenever we're faced with something. All right. So now you multiply it out. You say, all right. So when we talk about multiply out, we're talking about really doing a FOIL, and stands for first, outer, inner, last. But the key is, if you look at the first terms and the last terms, those will become pure real, right? In other words, there's no I. Where if you look at the outer and the inner, those will become pure imaginary. They have I. And so you split it into things which don't have I, things which do have I, and each of those is a solution. So we end up with cosine 3t times minus 2, 3. And so, right, that's the first. Subtract, now do the last, sine 3t, 0 minus 3. The minus here is because I times I is a minus 1. Now, the key, this is our solution number 1. And then we're going to have our second solution, okay, the outside terms. So we're going to have cosine 3t, 0, negative 3, and the inside terms. All right, that'll be sine of 3t times negative 2, 3. Okay, and here is solution number 2. All right, so we have solution number 1 and solution number 2. Now what we'll do is we'll actually mush them together. So if we were to do that, well, here we'd have minus 2 times cosine 3t, and then 0, and then 3 cosine 3t, and minus minus would be plus 3 sine 3t. Okay, so there's solution number 1. Solution number 2, cosine 3t times 0, and minus 2 sine 3t. Then downstairs, minus 3 cosine 3t plus 3 sine 3t. All right, good. Now, we're not going to be able to finish this problem on one page, and that's okay. Whenever you have e to the at, unless you get lucky, just the right kind of matrix, it takes a little bit of work. If you have the right kind of matrix, you can fly. But what's going to happen? Well, what's going to happen is that we're going to take these two solutions, and these two solutions are going to fill up the columns of a fundamental matrix. So now we'll write down that particular fundamental matrix. So it's not e to the at, not yet. Hold on, we'll get there in just a second. So, but we have phi of t, and we'll just copy it. So we have the first column is that first solution, and so write that down. And the second column is the second solution. So minus 2 sine 3t minus 3 cosine 3t plus 3 sine 3t. All right, good. We'll put this page to the side and come back to it when we need it. All right. Now, I said it's not e to the at, not yet. What do we need? Well, what we have is that e to the at is equal to phi of t times phi 0 inverse. So we need to figure out what is this, and let's carry out the multiplication, and then we'll have our e to the at. All right, so first step, what's phi of 0? The nice thing is, it's easy to plug in 0. Cosine of 0 is 1, sine of 0 is 0. So we're basically just looking for anything with cosines. So minus 2, that's a 0. Here we have 3, and here we have minus 3. All right, so there we go. Oh, I see, that was pretty quick. Minus 2, 0, 3, minus 3. And now the inverse. You can remember the process, but a lot of people are like, hey, I'm young. I have brain cells. I'll remember the formula. All right, great. Let's do the formula if you remember it. So it's 1 over the determinant. So that's 1 over 6. Or 6 subtract 0, so 1 over 6. And then what happens? Well, you're going to swap the entries. So minus 3, minus 2. And then you change the signs, 0 and -3. Now, if in doubt, just carry out the multiplication, right? So in other words, multiply this by that. You get 6 plus 0 times the 6 is 1, good. 0 and 0, that's good. -9 plus 9 is 0. And then you have 0 plus 6 times the 6 is 1. It works. All right, so what we need to do is we need to take this matrix times that. Okay. Well, I mean, the hardest part here is just going to be copying. So the actual mechanics aren't bad. It's just, well, there's a lot to write down. But once you get past that point, you're like, oh, the ideas here, they're not so bad. They're not scary at all. We just have to be patient, not rush ourselves, make sure we're doing okay, and make sure we're having a good time. If we're not enjoying it, what's the point? 1, 6, -3, -3, 0, -2. All right. This is e to the at. So, well, can we fit it? Well, let's be careful. Equals, I'll put the 1, 6 out in the front. Okay, so here we go. We're going to have -2 times -3 makes that a 6 cosine 3t. And then we're going to have -2 times -3 is another 6, but that will be 6 sine of 3t. So that's okay. Boom, boom. Good, done. Now, to go to this entry, because now we have 0 and then -2. So that'll make that a 4 sine 3t. Okay? Good. Now, moving over here, we're going to have -3 times that and -3 times that. Now, okay, so -3 times this, -3 times that. So let's think through it carefully. We'll have -9 cosine 3t. Here you get a +9 cosine 3t, and they will cancel. Poof, gone. Okay. Then you'll have a -3 times 3 sine t. So that's -9 sine 3t, -9 sine 3t. Those will combine, and so we end up with a -18 sine 3t. Okay. Now, the last corner. All right. Well, 0 times that, 0, and -2. So we end up with 6 cosine 3t -6 sine 3t. Well, we can multiply the 1, 6 through, and we come to our conclusion that e to the at is equal to, well, cosine 3t plus sine of 3t. Down here, get -3 sine of 3t. 4 times 1, 6. That's 4, 6. That'll make that a 2/3 sine 3t. And then we have cosine 3t minus sine 3t. All right. Now, there's a quick check, or really there's two quick checks we can do to help give us some assurance that what we did was right. Easy check number 1, plug in 0. You should get the identity. So when you plug in 0, notice that the sine terms go away. Cosine 0 is 1, so you end up with 1, 0, 0, 1. Good. Check number 2 is if you were to take the derivative and plug in 0, you should get back that matrix. All right, moment of truth. So, derivative of cosine, negative sine 3t, plug in 0 goes away. Here, derivative of sine would be 3 cosine 3t, plug in 0 gives us 3. Derivative of 2/3 sine 3t would be 2 cosine 3t, plug in 0, 2. Here, derivative of sine 3t, with negative 3 in front, would be negative 9 cosine 3t, plug in 0, negative 9. Derivative of cosine 3t, negative 3 sine 3t, plug in 0 goes away, minus, here would be 3 cosine 3t, plug in 0, negative 3. It actually works. Wow, that's cool. Who would have thought? Well, a lot of people would have thought. It works out pretty slick. Really slick, actually. Okay, now are we done? No, I shouldn't have taken this away. We found e to the at. That's the hard part of this problem. So we did the first part. The second part, well, solve. You have x prime equals ax, and x of 0 is this, negative 1, 3. All right, well, how do we do that? Well, the answer is we have the following. Our solution is going to be, you take e to the at times x0. Now, in our case, x0 was negative 1, 3. Okay, so again, the hardest part is just copying. But once you realize, oh, that's the hard part, it's just learning to be patient. You know, you can channel your inner sort of meditative state. Copying down my expressions. I am finding peace and tranquility in doing this computation. And then you're like, yeah, wow, I am calm. I am happy. Okay, so can we do this again? All right, let's try to do it in one step. It's okay if you take more than one step. Here you'd have minus cosine 3t, and that's the only place we get cosine, right? Because it's this times this. So we have, all right, minus cosine of 3t. And then we have minus sine 3t plus 2 sine 3t. See that? Minus sine plus 2. So that would make this a plus sine 3t. Yeah, minus 1 plus 2. Yeah, the math checks out on that one. Okay. Now, how about the bottom term? Well, for cosine, there's no cosine here. There is a cosine there. There's a factor of 3. So 3 cosine 3t. And then, what do we have? Well, we have a positive 3 sine 3t minus 3 sine 3t. And if you put those together, we get 0. And we're done. That's it. That's it. That's the whole answer. Wow! That's so cool! That's amazing! That's amazing! Okay. So, I guess we should put a box around it. And, wow. That turned out better than I thought it would. And you might say, what do you mean? I actually haven't done the computation before. I didn't know what the final answer was. But now I know. And wow, isn't that a beautiful answer? That is indeed a very beautiful answer. All right, good. Well, that problem wasn't the most necessarily computationally intensive. It took time, but, just be patient, and life is good. And we're past systems. And if we're past systems, that means we're ready for Laplace transforms. Oh, yes. Whoa. If you're going to have Laplace transforms, make sure you've got your table handy so that you can refer to it. All right, this is a two-parter. Wow, double the fun. So we'll start with part A. This is a two-parter where part A and part B are completely unrelated. So don't try to read too much into let me see if answering part B helps with part A. No. Part A and part B are just completely unrelated. This is purely a test of, do you understand how to use the table? All right. So what do you have? Well, we have t, e to the t, sine t, cosine t. And we're asked to do the following. We're asked to say, okay, find the Laplace transform of that. Now we're going to use our knowledge of things. Now, notice this has like a lot of functions multiplying together. And so initially it's like intimidating, like, wow, lots of things multiplying together. But say, hey, well, let's simplify it. We're absolutely allowed to simplify expressions. And we know things. So for example, sine t, cosine t, we should know, what is another way to write sine t, cosine t? Do you know it? I hope you do, because it's a beautiful expression. It's basically the double angle formula for sine. So 1/2 sine 2t. All right, so now, see, we've whittled away a little bit. So now it's not really 4 functions, it's really 3 functions. So we have a 1/2 t e to the t sine 2t. Now, here comes the interesting thing. How do we go about deciding how to take this Laplace transform? It turns out we say, hey, there's kind of 3 things involved. So sine, it's like, okay, we know how to handle that. But there's this t that comes into play, and there's this e to the t that comes into play. Now the thing is, t's and e to the t's are actually easy to handle, by their own. So e to the t, we can think of that as a shift, and that's what happens. So if you look at the formula sheet, our table, see how there's that e to the at f of t, that corresponds to a shift. Now the t, I'll go ahead and point it out to it while we're here, just a little bit further down. Multiplying by t is essentially like taking the derivative. So say, okay, so in essence, we have options. So there's a couple things we can do. We could take sine, do a shift, do a derivative, take sine, do derivative, do a shift, or we say, hey, we have things like t sine at, we can do that, do a shift. We have e to the t sine t to t, okay, take that, do a derivative. There's lots of ways. So in fact, there's multiple ways to do this. Now for me, well, I would probably say try to keep things simple, and I would think that shifting is probably going to be slightly easier than derivatives. So because we know how to do t sine at, that's on our list. It's good to be familiar with your list. And let's see, yeah, it's still on, we can still see it. And what do we have? Well, we get the following. We can say, okay, so the Laplace transform of our 1/2 t e to the t sine 2t. Well, let's be careful here. We'll come back to that in a second. Laplace transform of just the t sine 2t. We'll handle that first. I'm just going to copy it. So it's right there, and here a equals 2. So that would be equal to 4s over s squared plus 4 quantity squared. All right. Now, what does the 1/2 do? Well, adds a factor of a half. What does the e to the t do? Well, the e to the t just says shift everything. Now that's e to the at, so that's a equals 1. So we're going to shift everything by 1. So everywhere we see an s, put an s minus 1. So our answer would be, well, the 1/2 times 4 makes it 2. S, we're shifting because of the e to the t, so s minus 1. Downstairs, the s becomes s minus 1 squared plus 4 squared. And we're done. See? We were able to say, aha, push the sine cosine together. We know how to do t sine 2t, and then the e to the t causes it to do a shift. And that's the whole thing. Really, this is mostly just a matter of, do you know the table? And if you know the table, you get to like play around, like, I know how to use things. And keep in mind, there's many ways to do things. It's okay for you to say, oh, I see a way, but let me give myself 30 seconds. Say, is there another way? And if there is, that's wonderful. And if you don't want to, no problem. Go ahead. There are situations where there's multiple ways to do it. And sometimes if you see a simple way, fantastic. Good. Off to the races. And if you don't, well, okay, still off to the slower races, maybe. It's okay. Sometimes things take time. At the end of the day, you also don't want to spend the whole exam just saying, let me try to find a better way. If you see a way and you're running out of time, do it. Just do it. All right, part B. Find the inverse Laplace transform of 2s squared plus 2s plus 2, very 2e on top, over s cubed plus 3s squared plus 2s e to the 4s. Now, this has been written in a way to sort of throw us off. Well, we're not going to let them do that to us. Not to us. Come on. We don't deserve that. Now, you might say, well, what do you mean? That e to the 4s. That's kind of a strange way to write that. So what we really should do is we should really pull that off to the side. So what we have is that in part B, it's really 2s squared plus 2s plus 2 over s cubed plus 3s squared plus 2s, and then that e to the 4s is e to the minus 4s. And definitely put it to the side, just over there. And it's like, okay, I'm going to worry about you later. Now, what do we mean by worry about it later? The answer is that when you see something where you have a e to the minus as, there we go, see there? If you have an exponential function and you're doing the inverse Laplace transform, it's going to be a shift at the end. In our case, a equals 4, e to the minus 4s, so we're going to shift everything by 4 at the end. And don't forget, of course, the unit step function to turn it on. So it goes to the side. Worry about that later. And now the important part. This part is what we're going to do our algebra on. And the algebra thing is partial fractions. You better believe you're doing partial fractions on the exam. So you should be confident in your partial fraction skills. And you say, okay, all right, I want to be confident. How do I gain that confidence? Practice. Practice. But first thing is make sure you have it set up right. It should be polynomial over polynomial. So that's why you have to have that e to the minus 4s pulled out, because that's not polynomial. Say, okay, great. All right, I got you, Steve. What else do I need to do? Well, make sure you factor the denominator. Now notice, what can you do downstairs? Well, you can factor out an s, and you have s squared plus 3s plus 2, and keep going. Does that factor? Aha, it does. What does it factor as? S plus 1 and s plus 2. So that's actually a pretty clean denominator. And, there's no repeated roots. There's no irreducible quadratics. You're probably like, why haven't you been doing this all along? Why did you make us wait till now? Well, sometimes good things come to those who wait. All right, so our partial fractions. So you have 2s squared plus 2s plus 2 over s times s plus 1 times s plus 2. All right, equals. This is the important part. Make sure you got this. You have something over the first term, something over the second term, and something over the third term. Now we don't have to do, like I said, there's no repeated roots. Make sure you know how to handle repeated roots. There's no irreducible quadratics. Make sure you know how to handle those. But in our case, this is what we have. Very nice and clean. Clear your denominators. 2 times s squared plus 2s plus 2 equals a times s plus 1 times s plus 2 plus b times s plus 2 plus c times s plus 1. Now, in case you're wondering, how are you doing this? What just happened here? What just happened was we took this equation and we multiplied both sides by this denominator. So s times s plus 1 times s plus 2. So whatever is here, that's what you multiply. All right. Well, this is a choice. Excuse me. This is a chance where choosing wisely pays off really well. So what are some good choices? Well, let's choose s equals 0. 0 plus 0 plus 2 makes 2. And here we have a times 1 times 2. That's 2a. 0, 0. So we get 2 equals 2a, or a equals 1. That's great. What's another good choice? Well, negative 1, because that'll make terms go away. You'll have 2 minus 2 plus 2, which is 2. Here you'll get 0. At the end you'll get 0. Then you get minus 1, and then minus 1 plus 1. So you get minus b, or b equals negative 2. All right, and the third good choice is negative 2. And again, your good choice is what makes things vanish. 8, okay, got to be a little slow here. Negative 2 squared is 4 times 2 is 8. Minus 4 plus 2 makes 6. 0, 0. And here we have minus 2, and here we have minus 1. So that would make it 2c. All right, great. So what is c? c is positive 3. So what we have is that this expression, which is what we're trying to take the inverse Laplace transform of, is the same as, we haven't done any inverse Laplace transform yet. What we've done is get to something which is a little cleaner. So this is the same as a over s, so 1 over s, b minus 2 over s plus 1, and c, which is 3, over s plus 2. And I'm putting that to the side just to help us prepare. All right, so let's make a few more notes, and then we'll write down the answer, because that's how close we are. The e to the minus 4s, this is a shift by 4, so we're ready for that. 1 over s, what will that become? Well, we grab our trusty sheet here. 1 over s is actually high on our list. It's the first thing on our list. That's going to be 1. 1 over s plus 1, well, that would be down here. See how it's s minus minus 1? So that would be e to the minus t. So that's e to the minus t. And then your s plus 2, same logic, e to the minus 2t. Now, that's before we do the shift. So, here we go. What's our final answer? Our final answer is take 1, but we shift. Well, if you shift 1, it's still 1. All right, so we have 1 minus 2. E to the minus, shift. Now, what do I mean by shift by 4? So this would be t minus 4. All right, and then plus 3. E to the minus 2, t minus 4. Okay, that's the functions shifted. And don't forget that you have to have that unit step function, t minus 4. And there you go. That's it. That's the whole thing. See? That's not so bad. That's not bad at all. We could do that. Well, good. Good. Because that's exactly what we want you to do. All right. That was number 6, which means we're doing great. That only leaves us with 2 to go. And let's finish it up, right? Number 7. Use Laplace transforms to solve the following differential equation. And your answer should involve a convolution. Well, let's do a quick, short review. what is convolution? So convolution says the following, namely it's f star g, and what it is this sort of interesting integral, 0 to t f tau g t minus tau d tau. That's the idea of convolution. Now, why does this have anything to do with Laplace transforms? Well, because it does show up on our table. See that? F star g. And f star g is f of s g of s. So if you have two things multiplying together and you're doing the inverse Laplace transform, you can always do a convolution. All right, so there you go. So there's f star g of t. All right. All right, good. Well, we begin our process here. We have the following. We're going to take the Laplace transform of x double prime plus 4 Laplace transform x prime plus 20 Laplace transform of x equals the Laplace transform of f of t. All right, now, how do you do x double prime and x prime? Well, no surprise, it's on the table. So x double prime, you get your s squared x of s, s x 0, x prime is 0, x prime s x of x minus x 0. Okay, so doing that, so we have s squared x of s minus s times x of 0. Well, that's 1 minus our x prime is 0. So minus, and it'll be a minus 14. Okay? Plus 4 s times x of s, and then minus our x of 0, which is 1. And, well, that's it. Then plus 20 x of s equals, and what's the Laplace transform of f of t? Well, not knowing what f of t is, f of s. All right, great. Well, we can clean it up. So, namely, there's a couple terms with x of s. So that would be s squared plus 4s plus 20 times x of s. And now, we'll move the other terms across. So there's a minus s, that would come across as a plus s. Here we have a plus 14, and here we have a minus 4. So plus 14 minus 4 would be a plus 10. Move it across. Minus 10. And then, of course, our plus f of s. All right. Now, what happens? Well, s squared plus 4s plus 20, does that factor nicely? I don't think it does. Well, what can we do? Well, we can do complete the square. So this is the same as s squared plus 4s, and then we say, well, what would we need to add? Well, divide 4 by 2, that's 4. Sorry, divided by 2 is 2, squared is 4. That's what we need to add. Then you still have 16 left. So it's really s plus 2 squared plus 16. All right, so now we're going to divide. And if we do that, we come up with the following. Namely, we have that x of s is equal to s minus 10. Divide that by s plus 2 squared plus 16. And then plus our f of s, divide that by s plus 2 squared plus 16. And I'm separating it because this is, in the nice form, polynomial over polynomial. And here, well, we don't know what f of s is. We'll have to think about what to do about that one in a moment. Now, you're probably thinking, hey, ho, 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 partial fractions. But but actually you don't need to do any partial fractions. That's already been partial fractioned. There's nothing more to do. It's already in the form that you need. Unfortunately, it's not in the form that we can get something off our table. So if you look at our table, which, hey, I happen to have, you say, you know, s minus 10 over s plus 2 squared plus 16 doesn't quite fit anything on our table exactly, but it's close. You see, it's close to these pieces here. Notice that you have s plus 2 squared. Well, that's really s minus minus 2. And then k squared would be like 16. So what do we need to do? Well, what we can do is actually rewrite it. So in particular, see this s minus 10? Well, we can write this as s plus 2. And then we say, okay, we subtract 12. Now, why write it that way? See, if we covered up the subtract 12, you'd have s plus 2 over s plus 2 squared plus 16. And that does fit the table. If you cover up the s plus 2, you have a number over s plus 2 squared plus 16. And that also fits the table almost. Well, with a little bit of gentle, loving care. And so, we'll do that. Now, what about this part? Well, here is where the convolution comes in. You see, what we have is really two functions. The function we don't know, f of s, and this 1 over s plus 2 squared plus 16. Now, 1 over s plus 2 squared plus 16 is something that we can do almost. There's this little piece, you know, it looks very close to the e to the at sine kt. And the point is, you have two things multiplying together, which means it can become a convolution. Okay, so time to clean up. So here we go, cleaning it up. So this will be s plus 2 over s plus 2 squared plus 16. All right, minus. Now, upstairs, what would we ideally like? Well, if you look at the table, you'd want there to be k upstairs. Now, k squared is 16, k equals 4. We'd like there to be a 4, so we're going to put a 4 here. We say, well, we should have minus 12, so that says I should have a 3 in the front. And then this last part, again, just to emphasize what's going to go on, I'm going to do something very similar, where we have s plus 2 squared plus 16. I'm going to put a 4 and a 1/4 in front, and an f of s. And now, just to help set us up, we say, hey, all these pieces translate in a very nice way. So this part right here, this is e to the minus 2t cosine 4t. Here, you have e to the minus 2t sine 4t. And again, this is e to the minus 2t sine 4t. And I'm talking about the inverse Laplace. And this f of s would be f of t. Right? Because that's where it came from. So, our answer becomes the following. We have that x of t is, just work your way across, e to the minus 2t cosine of 4t. Now, don't forget the minus 3, e to the minus 2t sine of 4t plus 1/4. And now we pull out the convolution. This is going to become a convolution, so we're going to write it as a convolution. So it's the integral 0 to t. And well, one of these will have a function of tau, one will be of t minus tau. Probably put the tau into this. So e to the minus 2 tau sine of 4 tau f t minus tau d tau. And that's the answer. There we go. There we go. Wow. Okay. Well, this is it. I don't know. Sometimes you're like, ah, this is amazing. And like, oh yeah, it works. Okay, great. So there's nothing really surprising about this. And it's just a matter of just being patient, working it through. And in this case, we didn't have to do any partial fractions. Sometimes we do. But be ready. And of course, make sure you know convolution. In some sense, it's one of the tricky ones on the sheet because it tells you, oh, yeah, there's this F star G thing, but it doesn't remind you what F star G is. So you better know it because, who knows what's going to be on the test? Well, we know. But we're not telling because we want it to be a lovely surprise. All right, so that leaves us with one problem. One last problem to bring it home. Number 8. Give the recurrence relationship for the series solution to y double prime minus 2x squared y prime plus 3xy equals 0. And given that y of 0 is 4 and y prime of 0 is negative 3, find the first 7 terms of the series and write your answer in the form given. So in other words, we don't have to find the whole series, but we got to find the first initial part. Now the main part of this problem, really the main part of any of these problems, is saying get that recurrence relationship. That's the most important thing we need to focus our energy on. So how do we get there? Well, the nice thing is that when we start these problems, it's very mechanical. So there's not a lot of thought goes into it. So much so that you can almost do it without really having to think, right? Well, at the start, we know it's a series solution. So we write our series. Sum k equals 0 to infinity, ck x to the k. And we need y prime and y double prime. Y prime, that's the sum k equals 0 to infinity, k, ck, x to k minus 1, and y double prime, that's the sum k equals 0 to infinity of k times k minus 1, ck, x to k minus 2. Now, nothing dramatic happened here. We just took the derivatives. Take the derivatives term by term. All right, x to the k, I know how to take derivative of x to the power. No surprises. Now the next step, again, very mechanical. So you say, well, look, we've got y prime, y double prime, so put it into the right places. So I already start with y double prime. That's the sum, 0 to infinity of k minus 1, c sub k, x to the k minus 2, minus 2x squared, y prime, sum, 0 to infinity, k c sub k, x to k minus 1, and plus 3x times your y. Sum k equals 0 to infinity of c sub k, x to k. And now, the next things are, there's sort of like 3 things you should do. If you just follow this, you'll be fine. Bring in your coefficients in the front. Reindex, so everything has the power x to the something, and x the same something. And then pull off your first terms and write it as one big sum. Just, doom, doom, doom. And so, again, our first step is we're going to bring in our coefficients. So I'm talking about the 3x will come in, the minus 2x squared will come in. All right, so if we do that, we have the sum. And I will say, part of this problem is you do a lot of copying. And I'll warn you, I make copy mistakes a lot. So how do you get good at not making copying mistakes? Go slow. And just sort of like double check, like, yeah, okay, yep, everything's matching. Because the ideas, I think you're good on the ideas. You're smart. You understand how things work. But what can happen is if you're rushing, or, especially it can happen if you have bad handwriting. Now notice x squared times x to k minus 1, x to k plus 1, is it's easy to make a mistake. Say, oh, whoops. So we don't want to make mistakes, because mistakes are bad. That's places where we lose points. We don't want to lose any points. We want all the points. Notice that x to the power k, that's where we get x to the k plus 1. All right, so we need to do a little bit of reindexing magic here. And so, that was our next thing, right? Bring in the coefficients, go in for reindexing. So how will we reindex? Well, I like everything to be the same power. Now, you can make it be whatever you want. I'll just choose L. And so I'm going through for each one of my sums. Whatever x to the power is, I'm going to call that L. So on the first sum, L is k minus 2. On the second sum, L is k plus 1. And I know some people are like, but wait, I can't be both. Well, you can because they're individuals. Do this one first. And in this world, L is k minus 2. Then do this one. And in that world, L is k plus 1. There's no problems. No problems at all. All right, great. Now, if L is k minus 2, that's the same as saying k is L plus 2. Here, k is L minus 1, and k is L minus 1. All right, so on our first sum, we get the sum k equals 0 to infinity of, well, L, whoops, we're going to k. Not k, we're doing L, right? So let's see, L would equal negative 2 to infinity. Yep, we'll fix that in a second. Sorry about that. So that's why I was just talking about, be careful. A lot of it is copying errors. And so if you slow down and be like, wait, hold on, everything needs to be in terms of my new symbol. Then you're like, oh yeah, that's right. Everything does need to be in terms of our new symbol. Then that'll help you fix what's going on. Okay, so see, everything's now in terms of L. And basically the thing is just everywhere you see a k, replace it by L plus 2, and then just simplify. Minus, okay, our next sum, well, now we're starting at L equals 1 to infinity. And we're going to get 2 times L minus 1, C, L minus 1, x to the L, plus the sum L equals 1 to infinity, 3 C L minus 1, x to the L equals 0. Now, a little bit of good news will happen on the first sum. Notice that at L equals negative 2 and at L equals negative 1, we get 0. Right? Because you have negative 2 plus 2, 0. Negative 1 plus 1, 0. Which means just knock them out. We don't even need to consider them anymore. All right. Well, hey, that's good news for us. So now where to? Well, we can say, hey, we'll change it so we don't start at negative 2. We start at 0. Now notice they don't all start at the same place because this starts a little bit early, but just a little bit. So move that up here, and let's write what we have. So we now have the following. At L equals 0, we just have the first term. And what do you see? Well, you see 2 times 1 times C2 times x to the 0. So that becomes 2C2. Then, starting from 1, everything can go into one sum. Our one sum to rule them all. So, we gather our coefficients. L plus 2 times L plus 1 times C, L plus 2. Okay, that's the first one. Minus 2, L minus 1 times C, L minus 1. And then our plus 3, C, L minus 1, x to the L. And that equals 0. All right. So now we say, great. What's the punchline? The punchline is once you've put all the coefficients together, Now you can compare coefficients on the two sides. Well, on the right-hand side, all our coefficients are 0, which means on the left-hand side, all of our coefficients are also 0. So, we've got good news. We now know, for example, C2 equals 0. That's good. We had to find it. And then this part is really the key. And it's telling us how the coefficients will relate to one another in terms of the series solutions. In other words, this is that fabled, or if you like, that storied recurrence relationship that we're after. So we have for L greater than or equal to 1, because we're starting at 1, we can say L plus 2 times L plus 1 times C L plus 2. And there are both CL minus 1s here. So let's see, plus, if we write this out, that's minus 2L plus 2 plus 3 CL minus 1. So I just distribute the minus 2 and the 3. And that equals 0. Okay, so this is minus 2L plus 5. Now, move this across. We can say, okay, L plus 2 times L plus 1, CL plus 2 is equal to, when we move it across, it'll become 2L minus 5, CL minus 1. Or we could say, hey, CL plus 2 is equal to this expression 2L minus 5, divide by L plus 2 times L plus 1 times CL minus 1. All right, good. Now, for convenience, I prefer to re-index this in a nice way. So I'm going to make a little note here. So I'm going to re-index by, I'm going to set n equals L plus 2. So that becomes Cn equals, all right, and well, some of these are easier to compute than others, n minus 1, that's, because there's L plus 2, that's n, L plus 1, n minus 1. Now, if you think about this, L is n minus 2. So L minus 1, it's n minus 2 minus 1. That says Cn minus 3. So we go back 3 terms. Now the hardest part, okay, 2 times, well, it's hard enough that let me not do it in my head, so because I don't want to get myself in trouble. All right, where can I make a little side computation here? So 2 times n minus 2 and minus 5. Right, so that'd be 2n minus 9. Wow, that's a lot. Well, that's okay. So 2n minus 9. All right, good. And this is our recurrence. And notice, initially it was for L greater than or equal to 1, and this is for n greater than or equal to, well, 1 plus 2, which makes it starting at 3. All right, so here we go. We're ready. Now, we've got our recurrence relationship, and we also have some initial conditions. Okay, we're told that y of 0 equals 4, and y prime of 0 equals negative 3. Well, when we give these initial conditions, what are you really giving? So the value of the function at 0 is c0. The value of the derivative at 0 is c1. So we say, hey, great news for us. So this translates into saying c0 is 4. Here we get c1 is negative 3. C2 is up here. It's 0. All All right, what about C3? Well, now we break out our recurrence relationship. So C3, that would be 6 minus 9, which would be negative 3, divide by 3 times 2 times C0. Okay, well, the 3's cancel. 4 goes into 2, so that leaves us with negative 2. All right, that's nice. Okay, how about C4? Okay, so plug in 4. 8 minus 9 is minus 1. Then you have 4 times 3 times C1, which is negative 3. Well, the 3's cancel. Minus makes a plus, and so we end up with 1/4. All right, what about C5? Well, 10 minus 9 is 1 over 5 times 4 times C2, which is 0, which makes that 0. And remember, we need to get up to C6, so we're almost there. We're almost there. I think we have just enough space to squeeze it in. C6, all right, is what? Well, 12 minus 9 makes 3 over 6 times 5 times C3, which is negative 2. So you get 6 upstairs, that cancels the 6 downstairs, and you end up with minus 1/5. All right, and now we stop. All right, great. So the last thing is to write our answer like they told us to, which is, okay, so it's C0, 4, and then C1x, so minus 3x, C2x squared. We could write 0x squared or just write 0, or just not even write it. I'll just not write it. Well, let's go ahead and write it just so that nobody doubts that we did the computation. Then minus 2x cubed, and then plus 1/4 x to the 4th plus 0 x to the 5th minus 1/5 x to the 6th. And so there is the start of the solution. So that's not so bad. And this will be a fairly reasonable solution in the range close to 0. So we can actually get some good information. So there we go. What a fun problem. Great way to finish this test, at least, well, this practice test. And I hope you do well on the real test. Keep studying, keep working, and we'll see you again, I hope.